Good morning, students. In this topic we are going to deal Coulomb's law. A French scientist by name Coulomb has deduced an expression for the force between two point charges. Coulomb அப்படிங்கிற ஒரு French scientist ரெண்டு பாயிண்ட் சார்ஜுக்கு இடைப்பட்ட ஃபோர்ஸுக்கு ஒரு ஈக்குவேஷனை கொண்டு வரார். இது அவர் ஒரு எக்ஸ்பெரிமெண்ட் செஞ்சு அது மூலம் கொண்டு வந்த ரிசல்ட். லெட் அஸ் கன்சிடர் a point charge Q1 and a point charge Q2 separated by a small distance R. R12 is the unit vector from Q1 to Q2. Now the force on the second charge Q2 by the first charge Q1 represented by this symbol F21 vector. This is the general procedure to represent a force. That is, first number should be on the second charge, and the second one is by the first charge. Now F21, this is the equation derived by Coulomb, a constant K into Q1 Q2 by R square R12 cap. So this force is acting from Q1 to Q2, and this is the force acting on Q2. Here R12 is the unit vector from charge Q1 to Q2. So this is given in the topic Coulomb's law. Let us now see some important aspects of Coulomb's law. There are 8 aspects. Let us see one by one. The first one is the statement of Coulomb's law. From this equation, I can remove the constant and equality sign and the magnitude alone. If I write F21 proportional to Q1 Q2 by R square. From this I can define Coulomb's law. The force between two point charges is directly proportional to the product of the charges and inversely proportional to the square of the distance between the charges. So this is the first aspect, statement. The force between two point charges is directly proportional to the product of charges and inversely proportional to the square of the distance between the charges. Then the second aspect says about the direction of the force. The force acting on the second charge as given by this equation. Now what will be the force on the first charge? What will be the direction? So the Q2 charge will give a repulsive force from Q2 to Q1. Then as F21 is along R12 cap and F12, the force on the first charge by the second charge will be along R21 cap. In vectors we know that R12 cap equal to minus R21 cap. Only the direction is opposite, magnitudes are equal. So the two forces are acting along the line joining the two point charges, and the force on the Q2 charge is acting along R12 vector, and the force along the second charge is acting along R21, that is minus R12 vector. R21 vector equal to minus R12 vector. The third one states about the value of K. It is experimentally found that the proportionality constant K equal to 1 by 4 pi epsilon naught equal to 9 into 10 power 9 Newton meter square, Coulomb minus 2, where epsilon naught has a value of 8.85 into 10 power minus 12 Coulomb square, Newton inverse, meter inverse 2. And epsilon naught is called the permittivity of free space. Permittivity of free space. So this is the third aspect. And the fourth one, the force between 2 point charges each of 1 coulomb. Force between 2 point charges, if Q1 equal to 1 coulomb and Q2 equal to also 1 coulomb, and if they are separated by a distance of 1 meter in free space, then I can write this equation as F21, the magnitude alone, without vector. You can write this as for K, 1 by 4 pi epsilon naught, 9 into 10 power 9. Q1 into Q2, 1 into 1 by 1 square. So this is 9 into 10 power 9 Newton. This is a very huge force, equal to the weight of 1 million ton. 9 into 10 power 9 Newton is almost equal to weight of 1 million ton. Such huge force cannot exist, and therefore the charges will not be of the order of Coulomb. So therefore the charges that exist in nature of the order of micro Coulomb and the nano Coulomb. So in the fourth property states about the force of the order of 9 into 10 power 9 Newton between 1 Coulomb separated by distance of 1 meter. So this is the fourth aspect. Let us go to the fifth one. If the charges are placed in any medium other than free space, the constant K will be equal to 1 by 4 pi epsilon, where epsilon is the permittivity of the medium in which the charges are situated. So therefore, for any medium other than free space where the permittivity of the medium is epsilon, then the force I can write as 1 by 4 pi epsilon Q1 Q2 by R square into R12 cap. Here epsilon is called the permittivity of the medium. As epsilon, the permittivity of any medium is always greater than epsilon naught. The epsilon naught விட epsilon கண்டிப்பா அதிகமா இருக்கும். அதனால the force between the charges reduces by epsilon r, where epsilon r is called the relative permittivity. I define another quantity, epsilon r. It is defined as the ratio of permittivity of the medium to permittivity of free space. So as epsilon is greater, the force between the charges when placed in any medium is less than when the charges are placed in free space. So free space வைக்கிற force விட மீடியத்தில் வச்சோம்னா force கண்டிப்பா குறையும். எந்த அளவு குறையும்னா epsilon r அளவு குறையும். So this is the fifth one. The fifth one, epsilon and epsilon r. Force decreases by a factor epsilon r. Sixth one. This is analogous to gravitational law. The force between the Coulomb's law states about force between two charges, and gravitational force says about the gravitational force between two masses. Here we have two charges, in gravitational law we have two masses, that's the only difference. But there are four main differences between Coulomb's law and the gravitational law. Difference between Coulomb's law and gravitational law. I can tabulate the difference. Coulomb's law, gravitational law. The first difference is the force between the charges may either be attractive or repulsive. Attractive or repulsive, depending on the nature of forces. If both the forces are positive, both the forces are negative, there is repulsive force. If 1 plus and 1 minus charge is there, the force will be attractive. But in the case of gravitational law, it is always attractive. There is no repulsive force. The second one, Coulomb's law is very large, due to the factor that the value of constant K equal to 9 into 10 power 9 Newton. Newton meter square Coulomb minus 2. And gravitational force is very big, and the gravitational constant value is 6.626 into 10 power minus 11 Newton meter square kilogram minus 2. So the same distance, same force, the charge is replaced by mass. And the third one, Coulomb's force depends on the medium in which the charges are placed. This is independent of the medium. Independent of intermediate medium. எந்த மீடியம் இடையில இருந்தாலும் சரி கிராவிடேஷன் ஃபோர்ஸ் அதே அளவு தான் இருக்கும். பட் காத்துல வைக்கிற சார்ஜுக்கும் கண்ணாடிக்குள்ள வைக்கிற சார்ஜுக்கும் தண்ணிக்குள்ள வைக்கிற சார்ஜுக்கும் that force will vary. அதர் மீடியத்தில் வைக்கும்போது ஃபோர்ஸ் குறையும் அப்படிங்கிறது ஏற்கனவே பார்த்தோம். Then the fourth difference. The last only four differences are there. The fourth one is, in the case of gravitational law, this is the same whether the masses are at rest or in motion, independent of motion. Independent of motion of masses. But here, when the charges are moving, in addition to Coulomb force, another force called Lorentz force comes into play. Lorentz magnetic force. இங்கே சார்ஜ் மூவ் பண்ணாலும் ரெஸ்ட்ல இருந்தாலும் அதே கிராவிடேஷனல் ஃபோர்ஸ் தான், அதே லா தான். பட் இங்கே Coulomb's ஃபோர்ஸும் அதே தான் இருக்கு, பட் இன்னொரு ஃபோர்ஸ் எக்ஸ்ட்ரா வரும். That's called Lorentz magnetic force due to the motion of charges. So these are the four major differences between Coulomb's law and gravitational law. Coulomb force and gravitational force. Seventh one, we have already seen that in this case the two forces are opposite in direction. So the F21 force on second charge by the first charge is given by this I can write as K into Q1 Q2 by R square into minus R21 cap. Taking minus outside, I can write this as K into Q1 Q2 by R square into R21 cap. This is nothing but, comparing this is nothing but the force on the first charge by the second charge. From this, Coulomb's law obeys Newton's third law. So this is the seventh aspect. Aspect என்பது அம்சங்கள், முக்கியமான அம்சங்கள் என்னென்ன அப்படிங்கிறத இப்போ சொல்லிட்டு இருக்கிறோம். Seventh one, and it obeys Newton's third law. The last one, this law is applicable only for point charges. But point charges are ideal. No such charges are there. Charges are carried by bodies which have definite size, definite dimensions. But you can apply this law even to charged bodies. The size of the body is very small compared to the distance between the charges. So these are the important aspects. Let us recall the aspects alone. Statement: the force between the charges is directly proportional to the product of charges and inversely proportional to square of distance. And the direction of the forces on the second charge and the first charge are exactly opposite in direction. And the value of constant is 9 × 10 power 9. And epsilon is not, is called the permittivity of the medium, has a value of this much. We define another quantity. Sorry, epsilon naught is called the permittivity. Then we go for the force between 2 point charges of 1 coulomb and 1 coulomb each. The force works out to this much value. Such huge charge cannot exist. So therefore, the charges are of the order of -6 or -9 coulomb, microcoulomb or picocoulomb. And this force is almost equal to the weight of 1 million ton. And if the charges are placed in any medium other than free space, I can write the equation, the force for the force between the charges, by replacing epsilon naught by epsilon, where epsilon is the permittivity of the medium, and as epsilon is greater than epsilon naught, the force between the charges when placed in medium is less than when the charges are placed in free space. We define another quantity called epsilon naught, that is relative permittivity. This is defined as the ratio of permittivity of medium to permittivity of free space. Then we have seen the 4 differences between these two laws, and this obeys Newton's third law, and this is applicable only for point charges. Even though this is the case, you can apply this for the cases of charged bodies where the distance between the charged bodies is very large compared to the size of the bodies.